Dear colleagues, dear participants, it's my great pleasure to introduce our today's speaker, Professor Tomoki Ozawa from Tohoku University. Let me say a few words about his scientific career. He started this career from University of Tokyo, where he obtained bachelor degree, and then moved overseas to University of Illinois, where he obtained master degree and then also PhD. After a short period as a postdoc there, in 2012, he moved to University of Trento, working in particular with Sandro Stringari. After 3 years of postdoc, he moved to another postdoc to University of Brussels for another 3 years, about 3 years. And in 2018, he came back to Japan, where he worked in Riken as senior researcher, then from 2019 as postdoc researcher at GST, Japan Science and Technology Agency. And since 2020, he is associate professor at Tohoku University, and since the last year, he is full professor there, leading research group. The title of his talk is Recent Developments in Physics of Synthetic Dimensions. And we are glad that you are here, and we are looking forward to the talk. Please, Tomoki, the floor is yours.
Thank you, Andrew, for the introduction. Let me share the screen first. Yes, I think you can see my screen. Great.
Yes.
Okay. Good morning, everyone. So I first really want to thank the organizers, especially Andrew, for giving me this opportunity. And I'm very excited to give a talk here to contribute to the scientific education and research in Ukraine in the middle of this difficult time there. And I know that my contribution today is very little, but nonetheless, I am very happy to be a part of the activity to support science in Ukraine. And yes, as introduced, my talk today is about the recent developments in physics of synthetic dimensions. And so this is mainly about this concept of synthetic dimensions. And maybe many of you have not heard about this concept. I start from explaining what these synthetic dimensions are. So the definition of synthetic dimensions. This concept of synthetic dimensions have been developed mainly in ultra-cold gases and also in photonics. And in the second and third part of my talk, I will explain the developments in these respective fields about synthetic dimensions. Okay, let me start from the first part. What are synthetic dimensions? I forgot to tell you, but if you have any questions, you can interrupt me at any time. You can just, I think you can just ask questions, or you can maybe write in the chat. But you're welcome to interrupt me. Okay, so before explaining synthetic dimension, I need to explain what the dimension, what dimensions are. And we think for good reasons that we live in a three-dimensional world. Our world is three-dimensional. Okay, if you talk to some physicists, they may say that the world is four-dimensional, counting time as a dimension. That's totally fine. But so in this talk, I'll focus on spatial dimension. So I ignore time for the moment. And so talking about spatial dimensions, we live in this three-dimensional world. And the reason we think we live in a three-dimensional world is that an object can move in three directions, X, Y, and Z. And so that means that, let's say, if an object can also move in some non-spatial degrees of freedom, then we may be able to call these degrees of freedom also as dimensions. So that's the basic idea of synthetic dimensions. Okay, so what does it mean that to move in non-spatial degrees of freedom? And in physics language, it means that in the Hamiltonian, we have a kinetic energy term along that non-spatial degrees of freedom. So here, x, y, and z are ordinate coordinates. And there's the first term here is the kinetic energy along that directions. But here I have another degrees of freedom, which is labeled by W, and the second derivative term in W looks like kinetic energy term along this non-spatial degrees of freedom. Here, the coefficient here, m star, may be different from m. That means that we have possibly a different effective mass along that new dimensional degrees of freedom. But okay, so what I say an object can move in the direction is that if the Hamiltonian contains kinetic energy term corresponding to that direction. And in this talk, synthetic dimensions mean that the degrees of freedom with a corresponding kinetic energy term in the Hamiltonian. So this is a definition in my talk. Okay. And let me give you one example. I'll give you many examples, but the first example is the frequency of light. So light, electromagnetic wave, can travel in the three conventional directions. But you know that the light also has a property called the frequency, and frequency of oscillation. And the light can take many different frequencies of oscillation. And this can be, for example, can be considered as an internal degrees of freedom. And so if the light can move along the frequency direction, that means if the light can somehow change its color, change its frequency, more or less in a free way, and then that will serve as, this frequency can also serve as a synthetic dimension. I'll come back to this example later in the third part of my talk when we discuss synthetic dimensions in photonics. But this is a basic idea. So you identify some internal degrees of freedom, and we use that as a synthetic dimension. But here, the non-trivial part, which I have not explained, is how to make the light move along the synthetic dimension. So that's a difficult part, and that's a non-trivial part. But if that part can be somehow solved, then we can use this frequency as a dimension. But okay, I'll come back to this example later. Let me give you another example, which is a discrete synthetic dimension. In many cases, the synthetic dimension I'll introduce in this talk are discrete. So instead of having a continuous dimension, this synthetic dimension has discrete degrees of freedom, or lattice, has a lattice structure. And here, example I'm going to give is a rather trivial example. So consider a spin 2 particle, one particle in a magnetic field oriented along x direction. And then the Zeeman energy term of the Hamiltonian looks like this. So Zeeman energy looks like a magnetic field times the direction and the spin matrix along that direction. Here I'm applying magnetic field in x direction, so I need to take a spin x matrix and that matrix for spin 2 particle looks like this. I looked it up on Wikipedia, and so this is just a Zeeman energy term in the Hamiltonian. But this is also equivalent to the Hamiltonian of a particle hopping on a 5-side lattice. So let's say if you have a lattice with 5 sides and a particle hopping on the 5-side lattice with non-uniform hopping amplitude. Here it's b, here it's b times square root of 3/2. But then this tight binding lattice Hamiltonian, the hopping Hamiltonian, also takes this form. So you can regard this system either as a spin 2 particle in a magnetic field, or you can consider this system as a spinless particle hopping on this 5-side lattice along a synthetic dimension. So this is just two different ways to describe the same system. So we can choose the, let's say, convenient viewpoint to describe whatever physics or phenomena that you're interested in. And I'll give you more, let's say, non-trivial example why synthetic dimensions can be useful. But so this is a rough idea of synthetic dimensions. Sorry, so I have forgotten to tell you that I told in the beginning that the kinetic energy term is the important part, which will make the degree of freedom synthetic dimension. In the tight binding lattice Hamiltonian, kinetic energy term corresponds to this hopping term. So that's why I was talking about the hopping term in the Hamiltonian here. So if you have in a discrete dimension, if you have a hopping like terms in the Hamiltonian, then we can consider that degrees of freedom as a dimension.
Okay, so
Yes,
you interpret the ladder operator as the hopping here, right?
That's right. That's correct. That's correct.
Okay.
Yes, thank you.
Thanks.
Okay, so The question is, why should we care about synthetic dimensions? So maybe it's just a different way of seeing the same system and maybe nothing new. But the reason we want to consider synthetic dimensions, or we want to look at certain systems in the language of synthetic dimensions, is because it provides a powerful tool for quantum simulation, which is to realize Hamiltonians of interest and study their properties. For example, one may be able to realize models which are difficult to realize with other methods. For example, one may be able to measure observables and phenomena which are difficult to access with other methods. Some examples are the following. So for example, one may be able to realize topological models in a way different from how one would do in, for example, ultra-cold atoms or photons. I will explain more in next slides how to realize topological model using ultra-cold atoms as an example. And also, using synthetic dimensions, one may be able to realize models with 4 or 5 or higher dimensional Hamiltonians, which we cannot usually realize in this 3-dimensional world. And the synthetic dimensions also provide ways to realize, for example, non-Hermitian models or the model with very strange type of interaction. So this synthetic dimension is not a real spatial dimension. So you can have some strange interparticle interactions. So interaction does not need to decay as you go far in the synthetic direction. So that will give you some new type of interaction. And one may be able to also realize periodic boundary condition, or also the edge, with synthetic dimensions. So synthetic dimensions, one can, for certain synthetic dimensions, one can try to realize periodic boundary condition, which is not often easy to achieve in the conventional dimensions. So these are some let's say motivations to look at the quantum simulation with synthetic dimensions. Okay, so as an example, let me explain quantum simulation of quantum Hall Hamiltonian, which was kind of the original motivation why people came up with this idea of synthetic dimensions. So quantum Hall effect is an effect which was originally found in 2-dimensional electron gas under a perpendicular magnetic field. So there, Hall conductivity is quantized. And let's say we want to simulate or realize this effect in other systems such as ultra-cold atoms or photons. And a particle moving into the system under magnetic field obeys this kind of Hamiltonian. So P minus charge times the vector potential squared over 2m. And so this can be achieved for electronic systems by applying a magnetic field. But ultra-cold atoms or photonics, they're neutral. So neutral ultra-cold atoms typically use neutral atoms. That means this charge here is 0. That means if you just apply magnetic field, you cannot realize this Hamiltonian. So you need to do something more clever to realize such a Hamiltonian of a charged particle moving in a magnetic field. And same for photons. Photons are neutral. You apply magnetic field, and the Hamiltonian is different, like from this. And one way to realize this kind of Hamiltonian is in ultra-cold gases is to rotate the atoms. If you rotate the atoms, and if you look at the system in the rotating frame, the effective Hamiltonian in the rotating frame looks like this. So p squared over 2m minus the angular velocity and the angular momentum. And this you can write in this way. The last term here is the centrifugal force, and this first term here takes this form. So p minus something squared. So this something part plays a role of charge times the vector potential. So in this way, one can realize the effective magnetic field in ultra-cold gases, but as far as I know, people haven't really measured or observed the quantum Hall effect in such a way, because if you want to apply a strong magnetic field in this way, then you need to rotate the system strongly. That will also involve the strong centrifugal force, which you need to somehow compensate in the system. And So this is a way to realize effective magnetic field for neutral atoms, but it's often not very easy to, let's say, manipulate or to make the system stable. And for lattice model, the effective magnetic field appears as complex hopping. So this is a lattice, and let's say your particle, as it hops, it gets some hopping phase. And some of the hopping phase around one square correspond to the strength of the magnetic field. And okay, this is also not so easy to realize in neutral systems. You need some clever method, and there is a method which I'll mention in the next slides, but it often requires some effort. Anyways, but this line of research to realize quantum Hall effect in neutral systems led to the research field of synthetic magnetic field and synthetic gauge field. So that eventually led to the idea of synthetic dimensions. But before going to the synthetic dimension, let me explain some of the early attempts to realize synthetic magnetic fields for neutral ultra-cold gases. The important experiment was done by Ian Spielman group in the US in 2009, where they used Berry connection as a vector potential, Berry curvature as a magnetic field, or effective magnetic field, because it's not a real magnetic field, for ultra-cold gases. And there are also ways to induce complex hopping, which is necessary to realize a magnetic field in a square lattice, on a lattice system. And that can be induced by the proper time modulation of the system, which is called the method of Floquet engineering. And you can also shake the lattice in a circular manner to make also a non-uniform magnetic field to realize the so-called Haldane model. And so these research have been successful, and there's a good review on the artificial magnetic fields that you can read here. But along this line, some people came up with the idea that maybe we can use synthetic dimensions to realize the effect of magnetic field in neutral ultra-cold gases. And so this is the idea. So the original idea of synthetic dimensions was to use spin degrees of freedom of an atom as a dimension. So here, the x is a real dimension, and this m is a spin degrees of freedom. So different dots here corresponds to having different spin, or so z component of the spin in this direction. And so the important part is to make that particle move in that synthetic direction. So here it's the spin direction. The moving in the spin direction means there's some process to convert the spin, and that can be achieved in ultra-cold gases by applying two lasers in the proper polarization to make the atom with certain spin to have a different spin. So it's a hopping process that is induced by the applied photons. And if these applied lasers have some momentum difference, that will result in a multiplicative factor of e to the I times the momentum difference times x in the hopping phase. And that is exactly the kind of phase that you want to realize this kind of model, which models a two-dimensional lattice under a magnetic field. So theoretically, this idea to use the spin as a synthetic dimensions to realize this two-dimensional lattice model with effective magnetic field, this was proposed in 2014. And already next year, in 2015, it was realized in ultra-cold gases. So by two groups, one in Florence in Italy, another one is in US. So there they realized that, let's say, three-leg ladder or two-dimensional lattice model with three sides along the synthetic dimension. And they realized this hopping phase, which corresponds to having magnetic field in the system. And what's nice about this experiment is that there's a natural edge along this, along here and here. In ultra-cold gases, it's not very easy to realize edge in the system. Typically, people have harmonic or some kind of trapping which will smoothen the edges. But here, along this synthetic direction, you can have a sharp edge. And why it's nice to have sharp edge is the model that they're realizing is a topological model, which means that there's some modes that are localized at the edge of the system.
Tomoki,
Yes,
may I
please.
ask a question?
Sure.
So on this figure, I'm wondering whether the length of the synthetic dimension 3 is minimal one to realize H modes. So with with the length of 2, you cannot realize, or still.
So I think 3 is minimal. With 2, you can also see some kind of edge physics. It's not impossible, but you need some imagination or some analysis. With 3, you can, I think, understand the results more, let's say, naturally in terms of the edge states. But with 2, you can also see some chiral, let's say, physics there. That's also true.
Yeah. With 3, so you still have some one bulk.
Yeah, there's one exactly. That's right.
size.
Yes.
With 2, you do not have bulk.
That's right. Yes.
Yeah.
Yes. Okay.
Yeah.
Thank you. Okay, but these 3 sites along the synthetic direction, that's rather short, and many people like.
We have one more question. Sorry.
Yes, please.
From Professor Zvagin.
Thank you. My question is actually for higher spins. You have some magnetic anisotropy, which produces the periodic boundary conditions in your language, if you like. And it is unavoidable, as far as I understand.
So what's your question? So it's possible to realize periodic boundary condition by properly coupling.
Yeah, for sure.
Yes.
Yeah, that's for sure. For this spin 1 system, it is just rhombic anisotropy, and that's all. And it's very trivial. But I do not understand how to avoid this crystalline electric field for higher spins.
So you don't know how to. Sorry, what can you?
How to avoid how to use only so to say free spin without crystalline electric field, without spin orbit interaction, without anything else. That's my question. I do not understand it. Even for systems with ultra cold atoms, I don't think that there will be no crystalline electric fields.
So crystalline electric field. So I don't know what you mean by crystalline electric field. What do you mean by crystalline electric field? Sorry.
As usual, for any system, you have the surrounding of non-magnetic atom ligands, which produce electric field, and acting with this electric field on the orbital degrees of freedom, you have that's standard thing known since already for 100 years or so. Okay,
so you are saying that is necessary to realize this model in the end?
Yeah, but and for these kind of models, for some of these kind of models, you will have periodic boundary conditions in your language for this synthetic dimension, if you are speaking about. That is what I'm saying. Okay. And the other question, for this synthetic dimension, as far as I understand, the largest dimension of this will be something like 17, right?
It depends on what degrees of freedom you want to use. For spins, yes. For spin,
for spins, not for spins, for total moments. For spins, it is just 6, and that's all.
6.
For transition metals, the largest spin is 5.5. Right?
5.5.
I think not really, sorry, because, for example, ytterbium atoms, these are hyperfine states.
There it is the total moment, which is the good quantum number. There you have the largest value of the total moment is 8, as far as I understand. So 17, right?
Well, Oh, I don't know. Well, atoms also have the different spin states, different excited states. You can also couple them to make a longer.
Oh, you're speaking about high energy terms.
That's also possible, yes. And also this is not a like atom in a solid. It's an atom trapped in a vacuum, and you manipulate.
Yeah, but still electric fields are present, as far as I understand, isn't it?
Electric fields from the surrounding atoms?
From any sources, it doesn't matter. And spin-orbit interaction is present everywhere.
Yeah, spin-orbit interaction is there, but that's not really playing any role here.
Mm-hmm.
Yeah, spin.
Okay, maybe I will think about it, but
yeah, well, okay. There's some role play here to convert the spin of an atom using photons.
Mm-hmm. Okay.
Okay. Thank you for the question. I'm very happy. There's a lively discussion here. I'm very happy.
Thank you.
Okay, thank you. So yes. So coming back to this model with 3 sides along the synthetic direction. So this may look short, and the natural question is this a problem to have such a short synthetic dimension? And it depends. The answer is it depends on really what you want to look for. So what kind of physics you're looking for. So for some physics, of course, 3 sides are too short, but for some other physics, it's fine. For example, this is an energy spectrum of this previous model. So the lattice model is a flux, and it's plotted as a function of the magnetic flux. And it's called a Hofstadter's butterfly. And here I'm plotting 2 Hofstadter butterfly with one is ordinary one, and the other one is one with only 3 sides along the synthetic direction. And so the left one is ordinary Hofstadter's butterfly, so then it's spectrum as a function of flux. The right one, this one is the energy spectrum when there are only 3 sides along the synthetic direction. And I would say, okay, qualitatively speaking, they are similar. They look very similar. And so, well, it doesn't maybe mean much, but okay, maybe can tell you something that 3 sides are perhaps not a bad system, but bad lengths to look for certain properties of the system, which there's some resemblance, like a strong resemblance between this ordinary Hofstadter butterfly and the 3 sides one. And often, if you look at the topological physics, you can obtain a lot of knowledge, information from the 3 sides case. Okay, and I want to also mention the relations to parametric dimensions. That there's a very similar related concept of parametric dimensions. And here's the following. So let's say we have n-dimensional Hamiltonian in momentum space. So h of kx, ky, and so on. So there are n of this. And then one may replace one momentum by an externally controllable parameter. So I replace kx by some parameter phi. And then this new Hamiltonian is n minus 1 dimensional. So here in this phi is externally controllable parameter. It's not like a dynamical degrees of freedom. But with this kind of parametric dimensions, we can explore also some interesting physical phenomena. One is topological pumping that have also been experimentally measured in ultra-cold gases. Or one can even be more bold and try to replace all momenta by externally controllable parameters. So like all momenta are now replaced by some external parameters. And with this, you can also explore some interesting phenomena such as 4-dimensional non-abelian Young monopole that was realized in this experiment in Ian Spielman's group. This parametric dimension is different from synthetic dimensions in the following way, that the particles do not move along the parameter direction. So there's no kinetic energy term along the parametric direction. You can experimentally change it, but the particles cannot move there. in synthetic dimension that I was presenting in this talk, the particles can move along the synthetic dimension. So there exists kinetic energy terms along that direction. So that's a big difference. So in this presentation, when I say synthetic dimensions, I assume that there exists motion along the synthetic direction. That means there's some kinetic energy term along that direction. But I also want to say that this is just a matter of terminology. It's not very important. And I should say there's no consensus in the community. So some people call the parametric dimensions also synthetic dimensions, which I'm totally fine. But in this talk, I restrict to the case that when I say synthetic dimensions, I mean that there's some motion or the kinetic energy term along the direction. Okay, maybe I should also mention that this concept to study higher dimensional physics in lower dimensional platform also existed before the synthetic dimension idea was introduced in 2014. For example, in high energy physics, there's this idea of dimensional deconstruction or dimensional construction, in which they use multiple gauge groups to form dimensions. I should say I don't really understand what that means, but there are some ideas in high energy physics to study higher dimensional or to simulate higher dimensional physics, not really simulate, but to look at the higher dimensional physics in using gauge groups as synthetic dimensions in the current terminology. Also in condensed matter physics, there was idea to increase the connectivity of lattice to look for high dimensional physics. So by allowing the particles to hop to very far away size, you can effectively realize high dimensional systems using low dimensional platform. And there are also some study to find four-dimensional solitons in this lower dimensional world. And the 2014 proposal on synthetic dimensions using spins of ultra cold gas atoms was still quite groundbreaking, because first, it was a straightforward combination of existing techniques to realize synthetic dimensions to realize topologically non-trivial models or to realize synthetic magnetic fields. And also, soon after the theoretical proposal, experimental realization appeared, and that kind of made some momentum to study the synthetic dimensions. So that was say definition of the synthetic dimensions, and now I want to explore some developments of synthetic dimensions idea in ultra cold atoms. So I've already mentioned some examples in ultra cold atoms, especially the spin, to use spin as a synthetic dimension. I will introduce some other examples of synthetic dimensions in ultra cold gases. So one is to use momentum space like a real space. So okay, we can even use momentum space as a real space or the synthetic space. And for that, what we need to do is to have kinetic energy term in the momentum space. And Bryce Galloway from University of Illinois realized hopping in momentum space. So they have ultra cold gases and as some lasers with correct frequency and momentum and polarization, they can allow the BC to hop along the momentum space. So that will give you one-dimensional lattice in momentum space, and the BC can move in momentum space. And in this way, they can realize Schrieffer-Heeger model, which is a one-dimensional topological model, but in momentum space. And they could also realize its random version. So there's a random on-site potential called the topological Anderson insulator, and it has been experimentally studied by the Bryce Galloway's group and also some other groups in the world. And you can also use momentum space as a continuous synthetic dimensions. So here are my proposals. And the idea is to identify the harmonic potential energy. So this is a harmonic potential energy along x direction. This x operator can be written as the derivative of momentum. Now, but if you write x squared in terms of the derivative squared, then this looks like a kinetic energy. in momentum space. So that means if you apply a harmonic potential in real space lattice, and then focus on certain particular energy band, then the effective description of the physics on the particular energy band we are looking at takes the following form. So, this first term here is the energy dispersion, and this energy dispersion looks like a potential energy in momentum space. And the harmonic potential now looks like a kinetic energy in momentum space. And in general, if you have some energy band, there is a quantity called a Berry connection. Sorry, I forgot to write down the expression of it. But so this Berry connection acts like a magnetic vector potential in momentum space. So by using Berry connection and Berry curvature, you can even apply magnetic field in momentum space. And in this way, you can explore like Landau level physics, quantum Hall effect physics, and these things in momentum space. So using momentum space as if they are real space. Okay, another important example of synthetic dimensions is to use energy eigenstates as a synthetic dimension. So I again have a harmonic potential. And we know the harmonic potential, the energy level is equally spaced. So here the harmonic potential energy level is equally spaced here. And I want to use this equally spaced energy level of a harmonic potential as a synthetic dimension. So here I'm using energy eigenstates of certain lattice potential or the potential as a synthetic dimension. So what's important now is to allow particles to move along the synthetic dimension, which is to realize hopping along the synthetic direction, which is the energy eigenstates. So that you can achieve by shaking your potential. So here I have harmonic potential, and then I shake the system with frequency corresponding to the level spacing of harmonic oscillator levels. And this shaking with frequency corresponding to the energy level spacing translates into the hopping along the energy eigenstates. So here lambda is the energy eigenstate. And this shaking will induce hopping between adjacent energy levels. And then after some transformation, we can realize by shaking and going to proper frame, the Hamiltonian looks like a one-dimensional hopping Hamiltonian along this energy eigenstates direction with certain hopping phase. And combining this with a real space, so combining this synthetic dimension with a real dimension, we can realize a two-dimensional lattice with effective magnetic field, and you can, for example, look for some edge state physics there.
Sorry, Tomoki.
Yes.
Yeah. How you realize in real? So you introduce lattice in perpendicular direction to this harmonic potential.
I see. Okay. So, so you can, for example, imagine. Yes, you can imagine introducing lattice along the perpendicular direction. That's fine. Or you can imagine this harmonic potential as a part of a bigger periodic potential. So there's one potential here, and there's another potential here, which looks like harmonic when the energy is low. And then you can imagine hopping, enabling hopping between the adjacent trapping potential. So you can add lattice in either direction. Thank you.
Thank you.
So in this way, in principle, if you apply the harmonic potential in X, Y, and Z direction, then you can, in principle, realize 3 synthetic dimensions by applying harmonic potential in 3 directions. And by aligning this potential to form, let's say, 3-dimensional lattice, you can, in principle, realize, for example, 6-dimensional Hamiltonian in principle. Nobody has done it, but in principle, one can imagine doing that. Now, there is an experiment to realize these synthetic dimensions along the energy eigenstates. So I think this experiment, they use only one harmonic potential, and they observe the Bloch oscillation along the synthetic direction. So Bloch oscillation is a phenomenon where wave packet form in the periodic system under an electric field shows oscillation in real space. So here, periodic potential or periodic system means a periodic along the synthetic direction, and they observe the oscillation along the synthetic direction by shaking the trap in the proper way. And they experimentally measured the Bloch oscillation. Okay, another interesting phenomenon that one can look for in synthetic dimension is a higher dimensional physics. And one example I can give you is a four-dimensional quantum Hall effect. So two-dimensional quantum Hall effect was found in So two-dimensional quantum Hall effect happens in 2D system under magnetic field. It is known that analogs of quantum Hall effect exist in any even dimensions. So, but apart from two in the three-dimensional world, there's no possibility. But if we can combine with the synthetic dimensions, we can explore four-dimensional quantum Hall effect. A four-dimensional quantum Hall effect occurs, for example, in the following situation. So you have magnetic field in XY direction, and also magnetic field in ZW direction. W is a synthetic direction. And in such a setup, you apply electric field in a perturbative electric field in X direction, and also perturbative magnetic field in YZ direction, so YZ. And then you look for the force direction, which is W direction, and you look for the current response in the force direction. And this response is quantized to certain to the topological invariant of the system called the second Chern number. So this is a response of the 4D quantum Hall effect. And you can also study it using some concrete model. So this is a model that we proposed. So this is a four-dimensional lattice model. So this is a hopping Hamiltonian. And I have magnetic field in X, Z, and YW direction. And we did some numerical simulation of this response here. But in our numerical simulation, we assume that the fourth dimension only has 4 sides. So it's short and, let's say, realistic. And then we numerically simulated for the Hall response, which comes from the anomalous velocity term. So you apply electric field in one, magnetic field in 2 other directions, and you get motion in the fourth direction. And from that, we can numerically extract the second Chern number, topological invariant. And even with 4 sides, we can get a pretty good quantized response. So this is a numerical or theoretical work, but also there were experiments to realize 4-dimensional quantum Hall effect. The first ones came from this parametric dimensions. They use 2-dimensional real space and 2 external parameters to realize 4-dimensional topological pumping. So there's no dynamics in third and fourth direction, but they can still look for some 4D quantum Hall response in the setup. And there's also realization of 4D quantum Hall edge modes in electric circuits. Here, the fourth direction is realized by a long-range coupling. So by allowing the coupling to the to faraway sides, they could effectively realize a 4-dimensional setup in electric circuit setup. And they observe there's some 3-dimensional edge modes or the surface modes of the 4-dimensional system. More proper 4-dimensional quantum Hall response was recently observed by the experimental group in LKB France the last year. So what they did is to use 17 spins of dysprosium. So they have the 17 internal spin states, and using these spins, they realized 2 synthetic dimensions. So the 17 is divided into 2 synthetic directions. Then combining that with 2 spatial dimensions, they achieve 4 dimensions. And look at the response against synthetic electric and magnetic field to study for the quantum Hall effect. And there And the response, the quantum Hall response that they got experimental was quite good. Their second Chern number estimation was 0.97, 0.96, which is pretty good. And they also measured Berry curvature in many directions. So there are many directions that you can look for, and they experimentally estimated the Berry curvature in all these directions. Okay, so one thing I mentioned now is the difference between the real dimension and synthetic dimension. The biggest difference between synthetic and real dimensions is the interparticle interaction. So for ultra-cold gases with spins as the synthetic dimensions, the most studied form of the interaction is the following. So this is the on-site interaction of gases, where this nx is a number operator at the site that you're looking at. And here I'm summing over the spin states. So certain atoms have interaction of this form, and it has been studied in the context of synthetic dimensions. And this interaction has this feature that it does not depend on spin. So it doesn't depend on the spin labels, because here I'm summing over spin labels. That means this interaction is really non-local along the spin direction. And so here is the schematic drawing what I mean. So if there are like three particles that are distributed, for example, like this, and in the ordinary dimension, typically if the particles are closer, they interact more strongly than the particles that are far away. But if you use spin as a synthetic direction, and this x is the real dimension, then so this spin direction is synthetic. So in reality, in real space, the particles are distributed like this. So these two particles are close together. That means these two particles interact strongly, much more strongly compared to these two particles, which look closer in this synthetic dimension picture, but farther in the real space. So and the interaction in this two-dimensional real synthetic plane is rather unconventional. And there are some interesting physics that you can explore with this interaction. But at the same time, people also suspect that one can have some physics of short-range interaction, like fractional quantum Hall effect, to be observable under such interaction. So there's a pros and cons. So pro is that this is, let's say, new interaction that we can explore. The con is that we cannot apply the notion that we know from the short-range interactions. Well, this, I think, is the biggest difference between the real and the synthetic dimensions. Okay, so the third part, let me go to the developments of synthetic dimensions in photonics. I should say that since the synthetic dimension idea was proposed in ultra-cold gases, there are many proposals and also realization of synthetic dimensions in photonics. And here are some early ideas and also implementations of synthetic dimensions. The first one that I know is the optomechanics, where they used photon and phonon degrees of freedom as two sites. And a longer synthetic dimension for light was proposed around the same time to use orbital angular momentum of light as a synthetic dimension. And there's also, let's say, conceptually a bit complicated synthetic dimension idea, which is also very commonly explored, is arrival time of pulses as synthetic dimension. So they typically use two coupled fiber rings, and the light goes around these rings, and the part here in the middle is a beam splitter. So as light goes here, it splits into two. But the lengths of this loop and this loop are different, and that means if the photon goes here, that pulse will arrive earlier than the photon that went there. And this difference in the arrival time of the pulses can be effectively used as a synthetic dimensions. It's rather strange, and this beam splitter part works as a kinetic energy term. But this has been used and has been studied to realize various types of topological models or other models. There's also an idea to use eigenmodes of a resonator, frequency eigenmodes, which I'm being involved in, and I'll explain in more detail in the next slides. And there's also an idea to use spatial eigenmodes. It's idea and also the experimental verification to use spatial eigenmodes as a synthetic dimension. And there are also many more that I couldn't explain here. So there are many ideas and also implementation of synthetic dimensions in photonics, and it is quite an active area of research, I would say. And among these, I want to especially highlight this frequency synthetic dimensions, partly because I'm being involved in it. And so this is the idea to use a resonant modes of a resonator as a synthetic dimension. So let's say there's some resonator. Resonator typically have many resonant modes, and if you choose right part of this resonance, different modes are roughly equally spaced by the spacing called a free spectral range. Effective Hamiltonian around that area can be written this way. So this is a creation and annihilation operator of a photon at nth mode, and these are equally spaced by this omega FSR free spectral range. Okay, so to make the frequency a synthetic dimension, what we need to do is to allow photons to hop along this direction, and for that, we can modulate the index of refraction of the resonator with the frequency equal to the free spectral range. This is very similar to the proposal in ultra-cold gases to use the energy eigenstates as a synthetic dimension. So you have some equally spaced modes, and you shake or you modulate something with the frequency corresponding to the level spacing. And then, similar to the previous case, the coupling between adjacent modes is introduced, and then after going to the proper rotating frame, then what we get is a one-dimensional tight-binding lattice model along this frequency dimension, and possibly with some hopping phase. Hopping phase comes from the phase of the modulation. And so from one ring, you can realize one-dimensional lattice. And then by connecting resonators to form a d-dimensional lattice, one can realize d plus one-dimensional model with a frequency synthetic dimension. So yes, so we proposed it in 2016, and around exactly the same time, the group in the Stanford also had a very similar proposal. So apart from looking for some high-dimensional phenomena like a four-dimensional quantum Hall effect, with frequency, with synthetic dimensions in photonics, one can imagine realizing a device combining synthetic dimensions and topological physics. So it can potentially be useful. And for example, this is one idea that we propose in our paper. So if we realize a topological model, then there's some modes which are localized at the edge. If the input frequency of the light at an edge is resonant with one of these edge states, then if you insert light here, it goes down. If you insert light here, it goes up if they're resonant with edge modes. Here, x direction is a real dimension. This w is a synthetic frequency dimension. And then let's say we make one resonant mode very lossy, maybe coupling that mode with some other system. And then this lossy mode turns out to act effectively as an edge. So if you shine light here, the light wants to travel down, but there's a lossy mode and the light sees this as an edge and it turns here. Or similarly, if you excite here, the light wants to go up, but it turns. And that means that if you insert the system with if you insert light at the frequency right below the lossy mode, it from the right it goes to the left. But if you insert at the left, it goes down and it doesn't travel to the right. In the real space picture, if you excite here at the left edge, it doesn't travel to the right. But if you excite right, it travels to the left. So light only goes from the right to left. So it can be called the optical isolate. Optical isolate is a device where light goes only in one direction, but not in the other. Sorry. Yes,
May I ask question?
Yes,
Yeah.
please.
So if you decrease the loss rate, can you observe the edge current then circular? So I see that you have circles on the figure to the left that go down, right?
Yeah.
Okay.
It goes down or yeah. But in the synthetic frequency dimension, in principle, there's no edge. Sorry. So it keeps going down. In reality, there is some dispersion which will give the light some potential, so it will turn. But okay, so ideally there's no edge here, so it keeps going down.
Okay. Thanks.
Thank you.
One more question.
I may ask you such a question.
Yeah.
When you're talking about discrete dimensions, synthetic dimension,
Yes.
should these points be equally had equal distances?
To the first approximation, I am assuming that these are equally spaced, but in reality there is some dispersion. That means there's some deviation from the equal distance, and this deviation will act as an on-site potential in the effective lattice language.
Thank you.
Thank you. Okay. And this synthetic frequency dimension has been experimentally realized. The first experimental realization that I'm aware of is from the Stanford group, where they realized a one-dimensional frequency synthetic frequency lattice from one resonator. What they use is a 15-meter long fiber ring resonator. So this is a 15-meter long resonator, but they modulated the resonator correctly and coupled different resonant modes to measure the band structure along this synthetic frequency direction. So they measure the band. Okay, one-dimensional band structure along the synthetic frequency dimension. And around the same time, the Technion group realized the two-dimensional synthetic lattice, one real and one synthetic, using spatial eigenmodes as a dimension. So they couple different waveguides, and they'll also have energy eigenmodes, which they designed to have equal spacing, and by modulating the waveguide, they coupled different modes, which are eigenmodes, which is spread in the real space, and then they even realize a topological model to observe an edge state in this synthetic two-dimensional lattice. And there are further experimental developments in these directions, and these are not exhaustive. So there's some representative cases. For example, people could realize a two-leg ladder using clockwise and counterclockwise modes as a resonator as two legs. Or they could also realize two-dimensional synthetic lattice, observation of Bloch oscillation, and realization of non-Hermitian Hamiltonian, creating an edge in the synthetic directions, realization of the one-dimensional Schrieffer-Hilger model, and also measuring its topological invariance. And lattice with a lot of synthetic dimension sites was also realized. And synthetic dimensions can also be explored in the context of integrated photonics. These are the experiments that I've been involved in. So frequency synthetic dimension with silicon photonics was realized by the group in Yokohama and Tokyo. What they could realize is a one-dimensional band structure under an artificial electric and magnetic fields. They measured the band structure. And also, frequency synthetic dimensions was realized with lithium niobate by the group in Australia. And they could also measure rather complicated one-dimensional lattice, and they observed the band structure there. And one can also study some interesting physical phenomena like quantum Hall effect using synthetic dimensions in photonics. An analog of the quantum Hall effect, quantum Hall response, has been recently realized by the experimental group in Montreal, and with synthetic dimensions in photonics, using arrival time of pulses as synthetic dimensions. So this synthetic dimensions that if the pulse arrives earlier than the other, then it's in a different position. So this kind of a bit abstract synthetic dimension, but they could still realize this kind of lattice model, two-dimensional lattice model, and they could also control the hopping phase to realize topological model, topological Chern-Slater model. And they observe the band structure and also observe the quantized transverse displacement. That means, so if you have a effective magnetic field in 2D, you apply a force in one direction, your wave packet deflects in the other directions, the perpendicular directions. And they could change also topological nature. Here, what they realize is the Chern number -1, Chern number +1, and its Chern number 0. And depending on the topology, the deflection of this wave packet or the photonic cloud is in opposite direction. And from this displacement, they could also estimate the Chern number. And here the estimation is 1.01. Here it's -1. It's very, very close to the theoretical value. Sorry. And here's some possible outlooks on synthetic dimensions. First, to look for some many-body physics. So as I explained before, the interparticle interaction is a bit strange along this synthetic direction. And one can ask like two different questions. One is, can there be some interesting phenomena due to this strange interaction along the synthetic dimensions? And sorry, I forgot to cite, but there are some interesting studies in that direction. And another question you can ask is, if you can realize the short-range interaction along the synthetic dimensions, to look for some conventional physics that we're used to. And here's my proposal to realize short-range interaction. There's also another proposal. So if you can realize short-range interaction along synthetic dimensions, then we can explore, for example, fractional quantum Hall effect or some other many-body physics that comes with the short-range interaction. Under outlook, higher dimensional condensed matter physics, there are some experiments and theory on four-dimensional quantum Hall effect in synthetic dimensions, but these studies are mostly integer quantum Hall effect. Maybe interesting question is to explore the four-dimensional fractional quantum Hall effect. If that can be realized, that may have a good application in, for example, the quantum computation using the excitations in such systems. And also, there are various topological band structures known to appear only in high-dimensional systems, and it may be interesting to realize these high-dimensional physics in the lab using synthetic dimensions. And more on the technological side, synthetic dimensions can be useful for some applications. So chiral edge states combined with synthetic dimension may be useful, for example, to realize frequency converter, angular momentum converter, or there's also a proposal to realize the mode-locked topological laser using synthetic dimensions. So the synthetic dimensions combined with some topological physics may lead to some interesting technological application. So here's a conclusion. So synthetic dimensions is an idea to use non-spatial degrees of freedom as dimensions to realize high-dimensional models in low-dimensional platforms, and have been studied in atoms and photons. And I don't know many, or I really don't know any proposals to explore synthetic dimensions in electronic systems. And I think there's some room for study there. If you can come up with some nice ways to explore synthetic dimensions in electronic systems, that would be really great. Okay, so here's some reviews that I have been involved in. Some of them are not only about synthetic dimensions, but okay, so here's some reviews that if you want to know more, you can check these. And here's some reviews about synthetic dimensions that I have not been involved in, but I know that these are good reviews. So if you want to know some other perspectives other than mine, you can check these. And I want to finally acknowledge my collaborators. On theoretical side, and many of the works have been done in collaboration with Jacob Carsotto from Trento, Hannah Price from Birmingham, Nathan Goldman from Brussels, and Odell Zuberber from Constance. And also experimental collaborators include Toshihiko Baba from Yokohama, Armanda Spartritis from RMIT University in Australia, Satoshi Yomoto from Tokyo, Yasutomo Ota from Keio, and Philippe Saint-Jean from Montreal. Okay, so this is the end of my talk. Thank you very much for your attention.
Thank you. Thank you very much for a beautiful and inspiring talk. We are open for questions. So, if I may, I'll start then. I would like, if it's possible, to say a few words more about realizing short-range interaction in these synthetic dimensions. If it's possible to say a few words, what about idea how to do that?
Yes, sure, yes. Okay, yes. So I can explain, for example, my proposal here, which is to use, again, a ring resonator. But here, this is a proposal to use frequency modes of the ring resonator. But to realize short-range interaction, what I want to do is to use a angular coordinate or the coordinate inside this ring resonator as a dimension. So it's a periodic dimension, and it's a coordinate inside this ring. That means if the light is at the same coordinate, then they can interact if there's some nonlinear material along the ring. So yeah, so that's a proposal that I made there, and I forgot the other proposal that I mentioned there.
Okay. Thank you.
Yes.
Sergey?
Tomoki-san, thank you so much for the beautiful and informative talk. So many different things can be described as synthetic dimension. Can you only briefly comment what can be and what cannot be considered as this additional dimension? And what are benefits of using this notion? For example, I would like to say that you mentioned Floquet engineering. This seems to be a convenient way to describe driven systems, but you can use different ways. For instance, the notion of rest states, right? Speaking about synthetic dimensions, what qualitatively different besides convenient description they give?
So yes, so there are several aspects to your question, and yes. So here, so I'm shaking the system. For example, for this energy eigenstate as a synthetic dimension, I'm shaking the system with some frequency. So this is you can consider or you can analyze the system using Floquet theory, and the result would be the same. And so, well, and it's actually essentially the Floquet theory that I'm doing here. But to look at this energy eigenstates at the dimension, we can map this system to the well-known system of topological insulator of the particle in the magnetic field. So this gives, let's say, a convenient way for human beings to understand how to manipulate or how to understand what's happening there. So it's a different view to the same problem that you can analyze with the, let's say, conventional method, but it also gives you a way to connect to other areas. So that's, I don't know if that answers some part of your questions.
It does. And what cannot be described as synthetic dimensions?
What cannot be described as? Well, there are some limitations to synthetic dimensions. One is One is, so if you need to choose the right degrees of freedom, and some degrees of freedom are too short, or some degrees of freedom are it's not very easy to manipulate. Or also, if you want to look for many-body physics, as I mentioned a bit during the talk, then the interparticle interaction is crucially important. But many of the many-body physics that people know cannot be really applied to, let's say, natural interactions in synthetic dimensions. So if you want to realize some conventional many-body states with synthetic dimension, you need to come up with some clever ideas. So let's say that's the limitation here.
Thank you.
Thank you. And Dr. Kovalev, maybe you have questions.
Yes, please. Can I describe well-known one-dimensional magnetic system, classical magnetic system, as three-dimensional, this synthetic system with one spatial dimensional, a two-dimensional, and two synthetic dimensional, one-dimensional classical magnet?
So classical magnet means a spin model.
Yeah.
Yeah. Okay. So spin model, it's a bit tricky. So today I didn't talk about spin model. So here I'm talking about tight binding model where the particle hops. So spin model, so if you, for example, look at, let's say, the magnon excitation in the spin model, then the magnon can hop around, and that can be mapped to this synthetic dimension picture. But if you just have a spin model, and then so for spin, there's no really a like kinetic energy in the spin model. Spins interact, but the synthetic dimensions, the key point is to realize or to have the kinetic energy term along these non-spatial degrees of freedom. And yeah, so I have thought about like how to use spin model how to describe spin model in terms of synthetic dimensions, but I have this difficulty that like, spins are rather not moving, and that's let's say difficulty that I have.
But when we have the usual classical magnet,
Yeah.
then for the system not the usual, but magnet with elastic magnetical interaction. In this case, we can the displacement of magnetic atom in one direction, in one space direction, and the motion of the magnetic vector. So we have usual one special dimension, and two magnetic dimension. Can we use this two-dimensional as a geosynthetic? Because it is a well-known physical situation without any words about synthetical dimensions. And what we can additional in this science of synthetical dimension?
Okay, I think I understand what you mean. Yes. So it's like a classical like limit of using spin as a synthetic dimension. So spin is discrete, but what you're saying is you want to use the continuous classical spin or yes as a synthetic dimension. I think that's possible. I don't know on the top of my head how the let's say the kinetic energy along this magnetic direction looks like, and if it exists naturally in your system. But if it exists, then you can look at the system as a three-dimensional synthetic space. And so what you gain by looking at the system in this way, I don't know. But what I can say is if the three-dimensional model resembles some well-known three-dimensional model with some interesting property, then by trying to look for some this three-dimensional phenomena, or you can translate this three-dimensional interesting phenomena into this one-dimensional setup and try to look for the consequence of this three-dimensional model. So what you can gain by this picture is if you can find some good mapping to some interesting and well-known three-dimensional model.
Thank you.
Thank you. Thank you.
Thank you.
So I do not see further questions. If it's not the case, let us finish the discussion. So let's thank our speaker again for wonderful answers, wonderful discussion, and great talk.
Thank you very much.
Thank you for the support and all the best in your future research.
Thank you.
Thanks everyone for joining us today. So hope to see you next seminar. Goodbye.
Thank you.
Bye-bye.
Bye-bye.
Nice report.
See you in 2 weeks.
Bye-bye.
Bye.
Goodbye.